Hello and welcome. Thank you for joining. My name's Darren Frazier and I'm the Vice President of Sales here at Crystal Instruments. I'm here today to present multi-resolution spectrum analysis. This is a novel technique for computing and improving the resolution of narrowband FFT spectra. We're pleased to be with you here today and to present this computational method, which was designed and patented by the team here at Crystal Instruments. Just a quick reminder, this content is copyrighted. It's against the law to copy, redistribute, record, photograph this information without previous authorization or consent. Okay, with all that being said, let's dive into some of the topics I'd like to touch on here today. The first thing I'd like to do is start with a review of spectral analysis in general. From there, I'd like to move into multi-resolution and explain what multi-resolution is and how multi-resolution works. I'd then like to follow that up with a few examples or applications. The first being a steel plate, the second being a plexi plate, and both of those being modal applications. The remaining two will be a random test and then a sign-on random test. And for those two, I have a little bit more to add on that second sign-on random example. In the end, I will go over our patent that we have on this technique, and I will close out from there. Okay, so let's go ahead and get started here. So to start, let's kind of go over some spectrum analysis basics. So in general, we collect data in the time domain, and we segment that data into pieces called blocks or frames. For each one of those blocks, we compute the fast Fourier transform, or FFT for short, which takes this information and converts it into the frequency domain. A distinct feature of the FFT is that it creates a uniform linear resolution across the entire frequency spectrum. And just to kind of display what I'm talking about here, you'll see that we use the, all ever-present and ubiquitous Cooley 2-key FFT, and we apply that to incoming time streams. And when we do that, as you can see there on the right-hand side, we get evenly spaced frequency resolution. That is frequency resolution across the entire frequency spectrum. So in other words, the frequency resolution is the same throughout the entire bandwidth of the sampled data. That may be 2 hertz, 4 hertz, 5 hertz. And the resolution that we get is dependent upon 2 factors. So that is the block size and the sampling rate. So choose a larger block size and the delta F, or frequency resolution, will decrease. Excuse me. Choose a larger block size and the delta F will decrease. This will be an increase in resolution. Choose a larger sampling rate and the delta F will increase. And it may or may not go without saying, but a smaller delta F is preferable as it allows for a clearer picture into the ongoings of the application. So, and we'll show some, examples of that in later slides, and we'll have some exaggerated drawbacks of an overly or overtly large delta F. So with all this in mind, where we're coming to this is, in order to improve the frequency resolution and to provide a smaller delta F, you typically need to either increase the block size or decrease the sampling frequency, or both, of which will result in 2 things. One, you have a longer amount of time to collect each block, or you have more computational resources that need to be provided to increase that sample rate and block size. Now, the issue with a linear frequency resolution, as we've laid out here, is that in practice, a lot of times you need a smaller delta F so that you can resolve signals in lower frequencies, but you don't need a smaller delta F or higher frequency resolution in the higher end of the spectrum. So typically, you need better resolution at the low end as opposed to the high end. And again, I'll show some slides here in a moment and explain sort of why that is. So with that said, and with sort of this understanding of where we're coming from on current spectral analysis and how the FFT is applied, let's now sort of change gears and move into multi-resolution spectrum analysis. That is a technique we can apply to sort of improve or overcome that resolution at the low end of the spectrum. Multi-resolution, how does it work? Well, we start off with an incoming time stream, and we sample it as we would any time stream. And as we sample it, we then break that time stream up into blocks or frames. And from those blocks and frames, we then we take one block and we apply an FFT to it, just like we originally would. However, in parallel, we take that same block and we apply a decimation filter, and then we apply an FFT to it. So we sort of have two FFTs side by side that we have computed as this time stream's coming into our analyzer. Well, with that decimation filter applied and then the FFT taken, we now have, and with the decimation filter, we have to choose, of course, a frequency somewhere in the midpoint, mid-span cutoff frequency. And when we do that, we can get a better resolution FFT because we've decimated that frame. So we can get a better resolution FFT down at the sort of halfway point of that spectrum. So we take that original FFT that we've computed, we take the decimated block or frame of the FFT that we've computed, and then we combine both of these FFTs together so that we end up with a spectrum that has a much smaller delta F in the lower frequency while keeping the original delta F for the higher frequency of the spectrum. Now it's a little bit more sophisticated than that, and there's a lot to this, but in short, that's what's being done computationally to achieve this result that we have here that we're calling multi-resolution spectrum analysis, or MR for short. Okay, so with all of that, let's maybe talk a little bit about some examples to kind of highlight the benefits of this, and so that we can see this in practice. And the first example I want to go through here is what I have here on the screen, and that is a modal analysis example. So we took a steel plate and we hung it from a supported structure so that it had a free boundary condition. We used a modal shaker with a Hanning window and white noise to excite the steel beam. When doing that, we sampled, because of the fact that the steel plate was a lightly damped structure, we decided to sample out to 51.2 kilohertz with a bandwidth of 23 kilohertz. We chose a block size and spectral line resolution of 4096 and 1800, and this produced an initial or original FFT with a delta F of 12.5 hertz. So with multi-resolution enabled on this, we could get the lower portion, that is the 2.1 kilohertz or 2.8 kilohertz and below, down to a spectral resolution of 1.56 hertz. So much better than the 12.5 hertz we originally started with. What you'll see off to the right-hand side there is two plots. The upper plot has the magnitude and phase of our modal test. And what I'm calling out there is I'm just circling the lower half of this test from about, I think that's about 500 hertz. I don't know if you could see that, but about 500 hertz all the way up to that 2.8 kilohertz, so 2,800 hertz section. And the reason I'm zooming in on that section is because, again, that's the lower half of this FRF that will depict the sort of comparison between our multi-resolution spectrum and our regular FFT. And just to point out, the multi-resolution spectrum is the green curve and the blue curve is the regular FFT. And we're going to blow that section of the FRF up here in just a moment. So here off to the right-hand side, you can see that there's that section from about 500 hertz to 2,800 hertz, where our decimation filter cutoff was. And with that, you can see that there are kind of a larger difference between the multi-resolution spectrum and the original FFT spectrum. And again, that difference stems entirely from the fact that the multi-resolution spectrum is able to give us a delta F of about 1.5 hertz, where the original spectrum can only do at best 12 hertz. And we draw some distinction here to start with the Q value. So here you'll notice at the 960 hertz frequency, the 960 hertz resonant frequency, that we have almost a 7.7 times difference between the multi-resolution spectrum and the spectrum that does not apply multi-resolution. And that should kind of make sense because, again, with multi-resolution, we have so much more information that we can use with that higher resolution. And you'll see this again in the 1,400 hertz row, as well as the 1,789 hertz resonant frequency. And you'll start to see that we have these large, 7.7, 2.5 times, and then again, 46%. Now, it is worth noting that at the 2,453 hertz resonant frequency, we do see about an 81%. So it seems like we see an uptick there in the difference. And it's probably worth noting, it's a little bit beyond the discussion here as to why that is. I will just say that we did note that for this example. So the take home here is that a lower resonant frequency, you get a much higher Q value with multi-resolution spectrum analysis. And so now I want to jump to sort of the second feature of these two FRFs that we want to compare, and that is the damping. And this should probably be right in line, or should not be surprise that the damping here is also 7.5 times off on the 960 hertz frequency. It's 2.5 times off on the 1,418 hertz frequency, and 46 and 81% off respectively on the 1,789 and 2,453 hertz frequencies. And we're just noting this because, of course, of the significance that damping plays in modal analysis. But this should go hand in hand, obviously, with the Q factor, given that the Q factor will be a proportion of the damping. So 1/2 times the damping, I believe, will give you the Q factor. So the last sort of distinction we want to point out here between multi-resolution and a regular standard FFT run over this block or frame of data is the amplitude. So you'll notice that we're able to get a lot better amplitude values with multi-resolution than we are with a basic FFT. And this also shouldn't be surprising. We have more information with a higher resolution than we do with a standard 12.5 hertz resolution FFT. So we're able to more closely depict or represent what's truly taking place on this test specimen, in this case, the steel plate. And you'll see there we call out some of the differences between the two values. At the 960, the 1418, the 1789, and the 2453 resonant frequency values. But we don't just have to look at the magnitude of the FRF. We can also look towards the phase of the FRF as well. And when looking towards the phase, you'll see that there are also differences that we are able to call out, or that we are able to draw out. And there's every indication that a higher resolution is a better way of accurately depicting what's taking place with the test specimen. You'll see there at the 960 hertz, the phase difference is as great as almost 30 degrees. So the take home here, a sharper phase change estimate is provided with this multi-resolution technique. Let's jump now to a second example here. This is also an example of a modal analysis example, but in this case here, we're using a plexi plate or a plexiglass plate. Again, the boundary condition is free. We're hanging this plate. It's being suspended. The excitation in this case, though, is 2 shakers. We're using dual modal shakers, and we're lowering the sampling rate a little bit to 5.1 kilohertz with a bandwidth of 2.3 kilohertz. And the reason for that is simply because the plexiglass plate is a more highly damped structure than the steel plate. So there's just not going to be a lot going on out at the higher frequencies. And again, the lower frequencies are what we're interested in. So with all of that, we have a block size set to 2048 and a spectral line of 900. And that gives us a standard FFT of about 2.5 hertz. Well, if we, in like fashion, apply our multi-resolution technique or method, we can get a delta F or spectral resolution of about 1/3 of a hertz, or 0.31 hertz. And this is going to be with a cutoff frequency of our decimation filter at about 281 hertz. So 281 hertz and below, we are able to increase the resolution of our spectrum down to 0.3 hertz. Once again, the comparison plots here show in green our multi-resolution curve, and in blue our regular or standard FFT. And what I want to show here, or what I'd like to point out, is when you look at this damped structure, this plexiglass plate, and you look at that low frequency, I believe I'm down around 40 hertz all the way up to 280 hertz. And when you look over that band, you almost see that we've got 2 different graphs. Without multi-resolution, it's as if we're not even being faithful or being able to ascertain what the plexiglass plate is really giving us in terms of the FFT, or in terms of the frequency response down at that level. And so that's kind of why we wanted to draw this distinction. We won't go through as we did before, the Q values, damping, and the differences in the phase, but we did want to draw a distinction with this highly damped structure and the 2 different FRFs that result from it, just graphically. We should note that when we run a stability diagram on this data, both for the steel plate, and in this case here, we're looking at the plexiglass plate. When we run our curve fitting algorithm on this data, we see a large distinction in the stability diagrams of these FRFs. You'll see there off to the left-hand side, I have a stability diagram of an FRF with a regular FFT, and I have another one there with a multi-resolution FFT off to the right. And what we're showing here is that the stability diagrams indicate that the frequency and damping, the poles, are better recognized and called out with multi-resolution than they are with just a regular FFT that's applying sort of a larger frequency resolution, doesn't have as fine a resolution. I want to point out here that just because these poles are lining up better does not indicate that there is a resonant frequency here. It just simply suggests that multi-resolution will work to align the frequency and damping, or the poles that you receive from your data, so that if there were a mode, one of these pole alignments, the user would be able to call that out more precisely. So here, moving on to a third example, sort of an example outside of modal analysis, we come to another area of expertise for Crystal Instruments, and that is environmental testing, or in this case here, environmental vibration testing. And we call out a random vibration control test. And once again, we apply our multi-resolution spectrum analysis by separating the higher frequencies from the lower frequencies. And we sort of run two parallel calculations, and we run two parallel control loops. And by doing that, we once again are able to achieve a better frequency resolution at the low end without having to compromise on the increase in the computations that need to be done, or without having to compromise on the time it takes to run those computations. And I'm going to call this out. I'm going to sort of draw that distinction out a little bit further in a few slides from now. But I just want to let you know that when you're running a vibration control test, decreasing the computational time and decreasing the amount of time it takes to essentially compute the calculations required for the control loop, it's a very critical consideration for anybody running a vibe control test. So here on this same example of a random test, we can graphically see that if we just run a standard random test from 10 to 2000 hertz with a block size of 1024 and a frequency resolution of 400 lines, you're going to get a 5 hertz delta F, or a 5 hertz resolution across that entire spectrum. And recall, as we pointed out in that first slide, that this is going to be a constant, evenly spaced 5 hertz resolution. Well, if you apply multi-resolution, the multi-resolution technique we're calling out here, we can achieve a little bit over a half a hertz resolution down at that low frequency end of the profile. And that's important, because if we're trying to control, as we are there with the standard frequency resolution, we just don't have as many points that we can sort of pull on or operate on or filter to get that control to align with this profile. Now, it needs to be called out here that we chose this profile specifically to highlight the differences, and to highlight the differences using a high dynamic range profile. But this profile here is not uncommon. There are many tests down at the low frequency end of a random test that require a high dynamic range, that require that the control system achieve a high dynamic range. So we felt that this was certainly applicable in this case. Along that same train of thought here in the environmental vibration examples, we have here a sign on random test. This one here happens to come from Mill Standard 810. This is, I believe, method 514, Annex C. And in this test, this sign on random test, you can clearly see down there that we have a 17 hertz tone that is hardly resolvable using a standard 5 hertz frequency resolution. If we increase that frequency resolution using multi-resolution, you can see that we can get at least up to 8 times better, or a little over half a hertz resolution. And when we do that, the 17 hertz sine tone suddenly starts to become much clearer. Okay, well, let's move a little bit further with a, same example here, but instead of the Annex C section, let's move along the same lines to the Annex D section, where we now have 2 tones at 5.4 hertz and 10.8 hertz respectively, lower than the 17 hertz tone we had in the Annex C example. And so here, the problem is even more severe. Without using a higher block size, or without oversampling, you really need multi-resolution, because if you don't have it, you miss those 2 tones at 5.4 and 10.8 hertz respectively. You just don't have the frequency resolution at 1.25 hertz to see those tones at the low frequency. And you can see that there with multi-resolution, we can achieve up to a little over a tenth of a hertz, 0.15 hertz resolution. Now, we're talking about all this, and we're sort of saying, okay, look, multi-resolution has all these benefits, but some people might say, well, wait a minute, how did people run these tests without multi-resolution? Certainly these tests have been run without this technique, and how did people do it? And the short answer is, it just took a larger block size and a greater sampling rate to achieve the same results. And that can be done. We note, and you'll see here in these 2 video clips, small video images that I have, that you can achieve some of these profiles with a standard FFT, or standard spectral calculation. But in doing that, you have a larger computation that needs to be made. And in making that larger computation, you may have, in this case here, we show the distinction, a 6.4 second increase in the amount of time it takes to take in the larger block size and to oversample that data so that you can resolve those tones with a standard FFT. If you're using multi-resolution, we cut that down significantly. I don't have the time here, but we're at about 1/8 of that 6.4 second. In the next slide here, I've calculated a couple of the times and I put them into columns. So that's huge. If you're running a vibration control test and the user of that test, the operator of that test, notices that there's a problem, or even if the vibration control system notices there's a problem, this means it will take 6.4 seconds before that spectrum will update to register that problem and either shut down or pause that test. In this next slide here, I sort of lay out the differences between using multi-resolution, a larger block size, or trying to achieve the best of both worlds. So to the very left-hand side there, I sort of present a sign-on random spectrum without multi-resolution and with a low block size. So if you wanted to achieve sort of a fast 0.8-second loop time. You could do that, but you would have to adjust your block size down to 1024 points with 400 lines of resolution. No problem. You're not resolving though those two tones there on the lower end. So how do we do that? Well, we can do that by not using multi-resolution, but using a larger block size, which will, of course, give us a slower controlled response, and it'll give us longer pretest durations. And when we do that, we notice that, again, our control loop increases to 6.4 seconds. We've increased our block size by almost 8 times, as well as our lines of resolution at 8,192 and 3,200 lines. But we are able to achieve our delta F of about 0.15 hertz. Moving now to multi-resolution, where we sort of get the best of both worlds, we can apply this spectral technique, and we can get good resolution in the low frequencies and shorter block sizes. So we can use that 1024 block size, we can achieve that 0.8-second loop time, and we can get the decreased delta F or increased frequency resolution at 0.15 hertz on the low end and 1.25 hertz respectively on the high end. And so this we see as being a very significant improvement over the way things currently have been done with standard calculations for narrowband FFT spectra. With all that being said, I'm going to pause there on my examples, and I'd like to move now to sort of concluding and noting our contribution here for this technique. We had worked on this for quite some time back in 2018. At the end of 2018, beginning of 2019, February, we were granted the patent you see here. Of course, this was noted as a novel technique, which is the reason we received the patent. And we noted that there were a wide range of applications, a few of which we just talked about in the modal analysis area and in the environmental vibration area, environmental test and measurement area. But we do see that there are future applications that can be achieved with this technique. And we would just kind of sort of suggest that we're currently investigating and looking into applications for shock or classic shock, as well as shock response spectra. We're looking at this for the transient time history control that we run on our vibration controllers. And we're also looking at this for improvements in our time waveform replication. So with that, this is where we kind of see this going in ways that we think that we can leverage this technique for improved testing, certainly in the lab, but also in the field as well. These are a couple of the images we've submitted to the patent office on our technique and to give a sense for how it works. Again, the patent was granted earlier in 2019 after we had worked on this for a little over a year. And we're very proud that we were able to put this together. We will pause there for now and say thank you. We appreciate your interest in our work, and we thank you very much for being a wonderful audience and for joining us for our multi-resolution spectrum analysis overview.
Thank you so much, Darren, for all your information today. So now we're going to move on to our next presenter.